Welcome to our presentation on in-memory policy indexing in attribute-based access control. My name is Dominik Heutelbeck from FDK, and I'm also presenting on behalf of my co-authors Mark Lucas Bauer and Martin Kluber.
The presentation is structured as follows. First, I will present a short introduction and set the scope of the problem. Next, the problem will be defined in more detail and some related work will be discussed. Afterwards, the main algorithm for indexing access control policies in ABAC will be presented and I will discuss the predicate ordering problem. This is followed by an evaluation of the proposed algorithms and followed up with a short conclusion. First, let me briefly introduce the basic concept of attribute-based access control. ABAC is a logical access control method that controls access to objects by evaluating rules against the attributes of entities, such as subject and object, operations, and the environment related to a request. From this abstract notion, let's directly go into the practical architecture of systems implementing ABAC. Such systems usually control access to objects by subjects by deploying a so-called policy enforcement point into the code path which grants access to the object. The policy enforcement point usually communicates with a so-called policy decision point by sending an authorization request. The policy decision point is responsible for making the access decision, and this decision is based on rules contained in so-called policies which are stored in a policy repository. These rules may also refer to additional information accessed via policy information points, which may extend the information contained in the authorization request. Once the policy decision point has identified the right policies for making a decision with regards to the request at hand, it will evaluate the policies and then send the decision it made back to the policy information point, which will enforce the decision accordingly. Our research focuses on the process of identifying the right policies for a given request. So we are looking at the lookup from the policy repository made by the policy decision point. Therefore, let's zoom in on this process. The lookup of policies for a given request is usually governed by a so-called policy retrieval point. A policy retrieval point searches for policies applicable to a given request. This process is called policy indexing by XACML. Once the applicable policies are identified, they are sent back to the policy decision point, which then fully evaluates the rules contained in the given policies. This is called policy evaluation and checking. However, in the presented research, we are solely focusing on the problem of identifying applicable policies or policy indexing. This, of course, raises the question, when is a policy applicable to a given request? Therefore, we need to look into the structure of a typical policy used in ABAC systems. Typical policies expressed in a policy language like XACML or SAPL contains both a target statement and a block of rules. The target statement is what determines if a policy is applicable, so that the policy decision point only starts to evaluate the rules when the target is true. This is used for optimization, for example, to avoid I/O during the evaluation of rules, which may refer to attributes stored in an attribute repository or other information sources. Let's take a closer look at these target blocks. Here we have two target blocks, one expressed in XACML, one in SAPL, which both state the same requirement for being applicable. Both state that the current time contained in the environment part of the authorization request has to be between 9 o'clock and 17 o'clock. We can see that the target is a Boolean function over predicates of the request. Here the predicate is true if the time contained in the request is earlier or later than a given time. Overall, here the target is a Boolean function with an AND applied to the two predicates. Taking all this together, we can see that policy indexing can be reduced to a search in a set of Boolean functions. For a given set of Boolean functions, We are searching for those functions which evaluate to true for a given request. In the following, we examine how to construct an index which allows for efficient retrieval of such applicable policies. Then we will address the implicit predicate ordering problem we will find in this algorithm. A number of studies have been conducted examining such search problems or the indexing of XACM policies. The proposed methods would require significant modifications to be usable for policy indexing. The proposed XACML policy indexing approach by Ross will be subjected to a comparative study in the future. Now let me introduce you to the idea of the proposed algorithm. The basic idea is to count and eliminate conjunctions and predicates from the evaluation as early on as possible. This is based on a heuristic, taking into account the observation that policies in practice are designed for a specific application domain and that the target expressions will share some structure and predicates. In this way, the evaluation of predicates will allow to eliminate the need to evaluate other predicates. On the top level, the index is created by first normalizing all target expressions into a disjunctive normal form. Then a number of lookup tables is generated by counting the occurrences of predicates in conjunction in the different formulas of the target expressions. Finally, we pre-calculate an ordering in which the different predicates are to be evaluated for search. In this presentation, I will explain the algorithm using an example. We'll start with 3 formulas containing 5 different conjunctions and 5 predicates. Here I will focus on the main algorithmic ideas and leave out implementation details. The index contains a number of lookup tables. The values of the tables are looked up by either the conjunction or by the predicate in question. Let me introduce the individual tables. The first table counts the number of literals in each conjunction. The second one counts the number of formulas the conjunction is contained in. And the next table contains a list of other conjunctions which share formulas with the conjunction and in how many formulas these co-occur with a given conjunction. Then we have a lookup table containing a list of formulas in which the conjunction is contained to be able to quickly look up which formulas are satisfied as soon as the conjunction is satisfied. Then we provide 2 tables containing a list of conjunctions that become true or false if a predicate evaluates to true or false. Finally, we provide a lookup table from predicates to the different conjunctions in which they are contained. Overall, these tables can all be easily calculated by iterating over the formulas, conjunctions, and predicates. Also note that all these tables have to be recalculated each time the policies in the PRP change. While the index structure remains immutable during a search process, the search algorithm also maintains some state. First, we keep a table of the number of literals in each conjunction which are already true. Then we count the number of formulas that already have been eliminated from the search. Also, we keep the so-called candidate set, CW, which contains all the conjunctions which are yet to be considered during the search. The main loop of the algorithm iterates over the set of predicates in a given order. In this example, we will iterate from P0 to P4. With any given predicate, the algorithm will first check if the predicate is still relevant. The predicate is relevant if there is still a conjunction in the list of candidates which contains the given predicate. In this case, it is the first iteration of the algorithm, and of course, all of the conjunctions are still relevant, as we yet could not conclude that any of them is true or false, or if any formula containing them has been eliminated already. So here the predicate is still referenced by different candidates. Therefore, we evaluate the predicate, and here P0 evaluates to true. The next few steps of the algorithm can be implemented efficiently due to the given tables in the index. Please refer to the paper for the implementation details. Here I will only describe the basic ideas of what the different steps will try to achieve. So once we have evaluated P0 and know that it's true, we look up all the conjunctions which are automatically known to be true given P0 or later any previously known predicate value. We store this in CS. In addition, these conjunctions are also stored in CR, which is the preliminary result set containing all conjunctions which are known to be true, and therefore all formulas that contain these conjunctions will automatically also be satisfied. This set is updated in each iteration of the algorithm. Similar to identifying which junctions are now satisfied, we also try to deduce which candidates will definitely not be satisfiable with a given value of the predicate. As we now know that F2, for example, is satisfied, we try to deduce if there are any conjunctions which only appear in those functions that are already identified to be fulfilled and in no other. We call these kinds of conjunctions orphaned conjunctions, and we can safely eliminate them from the search. Next, we remove the satisfiable candidates, the unsatisfiable candidates, and the orphaned candidates from the candidate set. In this case, by evaluating P0, we were able to eliminate C3 and C4 from the search space, and we were able to identify that F2 will be satisfied. This identification of satisfiable, unsatisfiable candidates or orphans will continue while looping through the predicates. In this example, once we reach P4, the set of candidates is empty, and of course there are therefore no more conjunctions containing P4, and we no longer need to evaluate P4. Thus, the search concludes. Finally, the conjunctions contained in the result set are mapped to their corresponding functions. These functions are then the result of the search, and all the functions are satisfied given the value of the individual predicates. For the details of the individual sub-algorithms and for proof of correctness, please refer to the paper. There we also do worst-case runtime analysis, and we can see that the overall worst-case runtime is O von P times C plus C squared plus the overall predicate evaluation runtime. The order in which variables or predicates are evaluated is of utmost importance in many Boolean problems. For example, in designing efficient ordered binary decision diagrams used for chip design. In the paper, we propose an initial heuristic for choosing a predicate order. We're assigning a priority to each predicate based on an estimated likelihood of reducing the search space, as well as based on the cost of evaluation of the predicate. There are certainly a lot of opportunities for future work using machine learning approaches to optimize the predicate ordering at runtime of the system. For example, in the past I worked on optimizing variable ordering for OBDDs using genetic algorithms. For evaluation, we decided to use two different data sets. First, we generate a fully randomly generated set of policies, which is used because we try to eliminate any bias in the test data. Then we use a more structured approach where the policies are extrapolated from a realistic use case and where we expect more structure to be present for the algorithm to take advantage of. As a baseline, we compare our algorithm with a naive approach proposed by the XACML specification, where the algorithm would iterate over all documents stored in the PRP and check the target expressions one by one. The key measurement we are taking is the policy retrieval time. Note that for these experiments, only the target expressions are relevant. In the fully random case, we simply generate random Boolean expressions over a pool of potential resources, which are the stand-in for the predicates. For the more structured test data, we started by examining a realistic hospital use case, wrote policies for them, and looked at the characteristics of the different policies. Then we used these to generalize them and to generate a larger set of policies to upscale the scenario for benchmarking. Please refer to the paper for more details on the test data generation. Our benchmark results were very promising. For the fully random benchmark, we were able to reach an average speed up of 85% with up to 96% speed up, and for the structured random benchmark, we were reaching an average of 95% speed up with a peak of 99%. In this paper, we are presenting you with a novel indexing and search algorithm for policy retrieval points, applicable for policy languages like XACML and SAPL. The algorithm solves a more general problem of searching Boolean functions, which may have wider applications outside of ABAC. This research opens up opportunities for more future work in the area of automated policy optimization, predicate ordering optimization, and more empirical studies in realistic real-world applications, as well as comparative studies with other Boolean function indexing approaches and the XACML evaluation approaches of ROS 2012. Thank you very much for your attention. Please also take a look at the streaming attribute policy language at sapl.io.